Hi, we're Arya and Lian, and our project is on photon mapping with KD tree to render global illumination. Our motivation for this project is straightforward. We were inspired by those amazing renderings produced from global illumination using photon mapping. In particular, we're curious about whether extending ray tracing with photon maps could yield us a rendering image that more efficiently stimulates all types of direct and indirect illumination. For our project, we decided to implement photon mapping upon our basic ray tracer from assignment 4, and here are some of the references we based our code on. We set up a Cornell box similar to how scenes were set up in assignment 4. This Cornell box has one directional light source as shown by the right image rendering by the simple ray tracing with the shadows enabled. Our implementation follows the standard 2-pass algorithms. During the first pass, we release photons into the scene. In particular, for each light source in a scene, we allocate the number of photons based on the property of this light source. We recursively call the calculate photon path function while photons hit the surface and the depth is within our set limits. We store the photon if it hits the surface and use Russian roulette to decide how much of its energy is absorbed, reflected, and refracted based on the material properties. We build a KD tree of all the stored photons to speed up the rendering pass, since KD tree is especially ideal for handling non-uniform distribution of photons. In particular, we use the equation described in physical-based rendering to compute the weight of radiance stored in each photon. In our implementation, the weight is updated based on computed bidirectional scattering distributed function that computes the radiance, and the probability density function that is associated with the incoming direction of the photon. Following the paper, we implemented Russian roulette to terminate photon. This probability equation is chosen because photon will have a higher chance of being reflected if it's brighter. The condition of termination is set based on the comparison between a random value and the probability calculated from the weight of the photon. If the random value exceeds the probability, the photon path is terminated at that point. We save the constructed photon map into a point cloud file. The video here shows the 500,000 photons shoot into our scene. It is clear that areas that are blocked by the objects have less photons.
After finalizing the photon map, the second pass is rendering and computing radiance. We follow the rendering equation below, where FR is BSDF and LI is the incoming radiance. When calculating the incoming radiance, we use the incoming flux phi that is approximated using the photon map by locating the k photons that has the shortest distance to x, which is our pointed intersection. The value of k is specified in the command line as an argument. We use the KD tree to find a list of k photons around x. We can see this as expanding a sphere volume around x that contains k photons. To create a meaningful measure of incoming radiance, we use the density of the photons around x to normalize the incoming flux. We compute the circle around x with radius as the distance between x and the furthest photon. We project the sphere volume onto the surface using the area of the resulting circle. We then calculate BSDF of the material that takes into account two components, specular and diffuse. Our final reflected radiance is the product of the BSDF and incoming radiance. Here is the pseudocode describing our algorithm for the second rendering pass. For each pixel in the image, we cast the ray and check for intersection. At each point of intersection, we calculate the reflected radiance using photon map as described in the previous slide. This is a demo of what we described. The command line argument specified the number of photons, the value of k, and we used a smaller value to output the image for this demo. Here are the final renderings of the Cornell box with a larger output image. On the left, we set k as 100 and photons as 5,000. We can see that there are visible unevenness in the texture due to insufficient number of photons sampled at points of intersection. The rendering becomes smoother with 500,000 photons and 10,000 value of k. Here is a similar set of rendering with a sphere in front of the directional light source to show different illumination results. Even though our results are not perfect, but we learned along the process about how to implement a simplified photon map that renders indirect illumination results. We plan on improving our algorithm further to consider caustics and create more realistic results. Thank you for listening to our presentation.